Alright, we're almost there. Example 5. The limit as x approaches 0 of 1 over x plus 4 minus 1/4 all over x. So again, I'm just going to see what happens. So if I plugged a 0 in for x, that's going to give me 1/4 minus 1/4, which if that's all it was, we would be okay, but then we have that 0 in the denominator. So this is definitely giving us that beautiful 0 over 0. So now we get to try our last method we discussed, which is simplifying complex fractions by finding common denominators. Now, my hint to you as far as finding common denominators is often we're just going to end up taking the two denominators we do have and multiplying them together. So it's kind of, I don't want you to think cross multiplication because that's not what this is, but you kind of can flip-flop the denominator with the numerators as far as figuring out what to multiply by to get that one giant denominator. So in the first fraction, we're missing that 4. So we're going to multiply by 4 over here. And in the second fraction, we're missing that x plus 4. So we're going to multiply by that on the top and bottom. Now there are a lot of ways to do this. This is just the way I do, so feel free to use another method if that works better for you. Okay, so this is starting to look pretty crazy, and I'm going to go ahead and just add a really big parentheses because, like I said, it's getting crazy. It just helps me. Alright, so let's make this look less ridiculous. So now that they're both over this common denominator, we can just write them as one fraction. And one thing to just watch out for is you do need these parentheses specifically because you're subtracting that whole expression, not just the x. And now we have a fraction divided by another fraction, if we want to write it that way, which means we can simply take them out of the giant fraction and multiply by the reciprocal of the denominator. Alright, so I got rid of those parentheses by distributing the negative, and I multiplied by the reciprocal of our denominator, and this is where we can finally start canceling stuff out. So this 4 and this minus 4 will cancel each other out, and then this negative x, well, not the negative, but that x and this negative will also cancel each other out. So now we're left with the limit as x approaches 0 of negative 1 over 4 parentheses x plus 4. And now we can finally do direct substitution. And of course, 0 plus 4 is just going to be 4 times 4. So we have negative 1 over 16 as our final answer. Ooh, that's better. Alright. Alright, so our last example is a short one because, frankly, there's not much we can do. I see a quadratic which to me says I should try to factor it, but you'll see that this actually won't factor, which means I'm not going to be able to cancel out this factor in the denominator that when I plug in a 2 gives me something undefined. So when this happens, well, let's just try it. Let's just do direct substitution. So 3 times 2 squared plus 5 times 2, wow, my 2's are struggling today, minus 2 all over 2 minus 2. And what you'll see is this time we don't get 0 over 0. We actually get a number, I think if I remember right, it's a 20 over 0. So this is different than the previous examples because of that. And for right now, at this point in time, if this happens, you're just going to write that the limit does not exist. We'll discuss this in a lot more detail whenever we spend a day on limits that deal with infinity. But basically, if you have a limit like this where direct substitution yields a fraction with 0 in the denominator but not in the numerator, then this is going to be one of those cases where the limit is unbounded. So it's either increasing to infinity or to negative infinity, or straight up might not exist at all if it goes to two different directions from the left and right. All of those, however, still fall under this umbrella of limits that do not exist. And so until we spend a whole day discussing that in more detail, that's all you need to put. These are typically most common when we have those vertical asymptotes popping up, since this denominator didn't cancel out and is still a problem for us. But that should cover most of the examples you're going to come across for algebraic limits.